One of the key differences between DAX and the Excel formula language is that DAX lets you pass whole tables between expressions rather than just individual values. This can be really useful, particularly as it allows you to filter tables down before you do other aggregations on them. Alberto's going to go through this in a bit more detail about how you can use it to apply filters at different scopes, how you can use it to pull out distinct values from a table, and much more. One of the key things is that it allows you to actually create entirely new calculated tables that can be used just the same way as any other table that, for example, you pulled in from a database. Let's take a look at that in a bit more detail.
Speaking about related table, I started introducing the idea of a function that does not return a value, but returns a full table. If you are coming from an Excel background, this is a kind of function that is somewhat new because it does not return you one value to put into a cell. Instead, it returns you a full table containing rows of some table, and then you typically need to do something else on this table. You cannot simply take the result of a table and store it into a cell or show it in a report. You need to do something else. DAX is extremely powerful and has a very rich set of table functions. We don't have time to see them all, but at least to see the basic ones and get some feeling of how they work and what you can do with table functions. The basic table functions are only 4 or 5. You have filter, all values, distinct, and related table. We already spoke about related table, so you know what it does. I just want to introduce the other ones because you will use them very, very often and in most of your calculation. The result of table functions is typically used for other functions. You never publish it as a final value. And of course, the power of table function is that you can combine them in more complex way. Let's start discovering filter. Filter is very simple. For the next few demos or for the next few slides, I will not use the Contoso model. I will use a much simpler data model that only contains one table with these rows. So it contains orders. Oh, there I can read it. It contains the city, the channel, the color, size, quantity, and price, just those columns, and only 8 rows. And imagine that I create a measure that does a sum x over filter orders where order price is greater than 1. I put that into an Excel pivot table. This is not using Power BI. It's an old slide using still Excel, but there are many of them similar. And you see that for each cell, I see a different value. Let's see how it works. For example, to compute the value of this cell, 192, which is the value for green. When it's time to compute that value, the first thing that the engine does is say, oh, you're interested in getting only the green value and the internet value, because the slicer is filtering only internet, and on the rows I put the color green. So I'm not seeing the whole model, but only the 2 rows which are at the bottom that contain green and internet values. Then remember that DAX is a functional language, so in order to follow its behavior, you go to the innermost function, because sum x will iterate the result of filter. Filter will start iterating orders. So the first function that is called is filter, and filter says, oh, I'm going to iterate the orders. Remember that filter is an iterator. So filter iterates the order, and for each line, it checks if order price is greater than 1. On the first line, this is fine. On the second line, the order price is 1. 1 is not greater than 1. And so that line is not returned by filter. So the result of filter is a table, in this case containing a single row, that is then fed to sum x that computes quantity multiplied by price. Make sense? Yes. And the question for you, there are 2 questions for you in reality. The first one is, do we have a current row here? I guess you can, I need to get used to do that on both sides. You are just too many. Here. Yeah. Who says yes? Who says no? Blank is not a valid answer. So you will need to take a decision at some point, either yes or no. Who says yes? No. If I didn't have a current row, I could not even write order price. So I need to have a current row. And the current row here, which is providing the current row there? Louder. The filter iterator. That's fine. Filter is iterating over orders and is providing the current row. So this is the price of the currently iterated row by filter over orders. Okay? And do we have a current row here in the, let me see, I can reach it from here. Yes. We have a current row introduced by some x over the result of filter. Okay? So we have two iterations happening, one after the other. The first one is some x, is a filter iterating orders. The second one is some x iterating the result of filter. Okay? For the ones of you who come from a developer experience, typically people look at this and say, oh, iteration over a table containing millions of rows, this is going to be extremely slow. No, DAX is designed to work this way. So you can iterate billions of rows without ever worrying about performance. Performance issues in DAX never come from iteration, they typically come from other aspects. But feel totally free of iterating large tables. DAX is going to help you and write good code for you. So finally, the result is put on the pivot table. So filter is typically useful to add conditions. So it basically starts from a scenario and adds more conditions. It restricts the number of rows in a table by iterating over it and removing the rows you are not interested into. You might use it to compute the sum of products which are read, to compute the sales of whatever kind of filtering you want to produce. Filter is your best friend. But filter restricts the number of rows that your calculation performs. There is another function which is extremely useful, and you will use it many, many times, which is all. All that you can see here on some x over all orders quantity multiplied by price. All is a simple function that always returns a full table. So it ignores whatever filtering happened and always returns the full table. So if you write a measure that is sum x over all orders of quantity multiplied by price, then we follow the execution as it happened before. Imagine that we want to compute that number, 789. Initially, you have the same filter because you have a filter for green and the filter for internet, which are applied on the table. But then sum x requires the result of all. All wakes up and says, oh, guess what? There is a filtering on the sales table or on the orders table, but I'm going to ignore everything and return the full table anyway. So all always returns the full table. And once you have the full table, then sum x iterates over the 8 rows and computes quantity multiplied by price. That happens. Yes?
What if the filter is contained within the all? So you're saying all orders, but what if all contains a filter expression within it?
All cannot contain a filter. So the question was, what if all contained a filter? You can do a filter of all. That makes sense because you remove a filter and then you restrict it. You cannot do all over a filter just because all requires a table as an expression, and besides it wouldn't make much sense to add the filter and then kill it a few seconds later or a few nanoseconds later. You see that the number is the same in all the cells in the pivot table that show all orders. Of course, using all in this way, it doesn't make much sense to compute the same value for all the rows in a pivot table or in a report. But it becomes useful if you want to show values as a percentage. Imagine that you want to compute a value like the percentage of sales against all the sales. Then to compute that percentage, at the numerator you simply compute the sum of sales. At the denominator, you cannot compute sum of sales, otherwise the result will always be 1. So you compute the sum x over all sales of whatever you want to compute. And so you have at the numerator one number, and at the denominator the grand total of all sales. So all is not useful to create a measure like in this case that shows always the same number, but you can easily imagine that if you want to compute percentages, it makes a lot of sense. Okay?
How is all different than a related table?
Related table returns only the rows in a table which have a relationship with the current row, whereas a related all always returns all the rows. If we switch for a second on the demo machine, here on number of sales, if we switch for a moment on the demo machine, who's gonna list? Oh, here it is. Okay, number of sales does count rows of related table sales. If instead of having related table, I write all sales, then the result will always be the same value no matter which row I'm in, because it always returns the full sales of the model. Okay? Let's go back to the slides, thanks. So, sum x all ignores any filter that exists on the model. All is extremely useful. You can use all in two ways. You can use all with a table, and that returns all the rows of a table. And then all has a very special functionality that we will use again later, that you can use all passing a single column as a parameter. And if you pass it to it only a single column, it returns a table that contains all the possible values of that column, all the distinct values of that column. So all customers' customer name returns me one table containing one column and many rows, one row per each name of my customers.
So no duplicates? Duplicates are excluded?
Duplicates are removed, yeah. Only the distinct values of all the distinct values. If you want, you can use all with multiple columns, and in that case you get a table containing, in this case, channel color and size, and you get all the possible combinations that exist of channel color and size. It's not very widely used, all with multiple rows, but it's useful to know that you can do that, and it makes sense to have it as a functionality. In this case, it's only used inside the calculation, so it's not stored on the PBIX. It's computed during the calculation of your model, and then it's used to restore the value. Yep? It's coming in a few seconds. Values, we are going to speak about values in a few seconds. And then we are going to spend most of the afternoon spending time about values and what it computes. Yes, in that case you get all the existing combination of the three values. So if I do that, if I do all of customers, gender and customer name, I will get only the combination where I have a female name with female, but I will not have combination of male name with males. Okay? Hopefully, no, whatever. Sometimes you want to do all on many columns, and you want to only avoid a few of them, maybe only one. So you can want to do all of channel, color, size, quantity, price, amount, and you don't want to put city there. In that case, instead of writing the list of everything, you can do the opposite and say, well, let's use all except. All except orders order city does all on all the columns except on the city. Again, it's not very commonly used. I just wanted to show you it exists because we will use it probably later today. Of course, you can mix filter. You can write a filter of all of a table. And as an example, if you do a sum x over filter of all orders and then filter the orders where channel equal internet and then compute orders amount. Amount is a column which is not visible on the screen, which is the multiplication of quantity by price. If we follow the execution of this code, the first function that, imagine that we want to go there, we still have the filter for green, we have a filter for internet, so ideally we should see only these two rows, but then all kicks in, And all, it's the innermost function, the first innermost function, so it's the one which is executed. All returns always all the orders, and so it's going to return all the rows in the table. Then filter takes all the orders and returns only the ones where channel equal internet. So it will return those 4 rows, and this happens for all the rows. Finally, sum x computes orders amount and aggregates the value. So again, you see that we have the same value for all the rows that contain our internet. First, we remove any filter, and then we apply the filter that we want to apply. There is another function, which is called distinct, that returns, distinct is very similar to all, it's very similar to values. Distinct returns all the distinct values of the column you pass as a parameter. And it looks like it's very similar to all. The difference between distinct and all is that all ignores any filter, whereas distinct obeys any filter. So if I create a report and I slice by color, and then I take the count rows of distinct product names, I will get only the number of products of that given color. Whereas if I do a count rows of all product names, I will always get the count rows of all the products regardless of the filtering that is happening. Okay? Now, speaking about the number, the values returned by these tables, it's important to understand how many values does a column have. I know the answer is pretty simple. You simply count the distinct values of a column and then you are done. You don't need to know anything more. But imagine that you have a table like this one, amount, that contains the amount sold, and then product ID, 1, 2, 3, 3, and then 4. And then we have a product table. It's very clear, I'm Italian, by the product table, but what I consider a product, coffee, pasta, and tomato, anything else is not a product. And the product ID is 1, 2, 3. If you look at the sales table, of course, there is a relationship between the two tables. Now, for some rows, I have 1, 2, 3, 3. But for the last one, I have a 4. And 4 does not exist in the product table. So what would you expect at this point? The previous versions of analysis services, multidimensional, would complain about, oh, the data is wrong, I will never be able to process, and so you are going to get wrong results. The latest version, the current version, Tabular and Power BI, is much more relaxed and says, well, if your data is wrong, that's your problem. I will show you some numbers anyway. But I need to follow the relationship. Imagine that I slice by product. So I put the product in the pivot table or in the report, and I want the sum of amount. Do I expect to see this 14 somewhere? If I start slicing by product, 14 cannot be reached, so theoretically I shouldn't see it. Problem is that the total will be wrong. The total will not be the total of sales that I can grab from a different report that does not follow the relationship. So in order to solve this ambiguity and give some meaningful result, the engine does one trick, which is important to understand. That is, if the relationship is broken, because you reference values which are not there, it adds a new row to the related table, so to the table which is the target of the relationship, that contains blanks for all the rows, and then creates the relationship between the wrong row and the blank one. Make sense? And it's pretty clever, because in this way, if I slice by product, I will see coffee, pasta, tomato, and blank. So any user can see the blank and see the number which is of values unrelated to anything else. The point is, at this point, how many values does product has? It might have 3 values or 4 values, depending whether I count or I do not count the blank row. Now, some functions take into account the blank row, some others do not take into account the blank row. For example, all considers the blank row as a valid value. If I get all product, I will get coffee, pasta, tomato, and blank, so the result will be 4. Distinct, I never remember what distinct does. Distinct does not take into account the blank rows, whereas values takes into account the blank row. All takes into account the blank row, and there is another function that is all no blank row. It's pretty simple to understand what all no blank row does. All returns all the values, but does not return the blank row. Make sense? It's much less complicated than it sounds right now. You will get used to it. Of course, if your model is perfect, then all those functions return the very same value. If your model is not, you might be in trouble and need to define which function to use. Yep?
If you have multiple unmatched child records,
Only one blank row.
only one break, they all match.
Doesn't matter how many wrong rows you have in your table, there is only one blank row which is added. So if you have 100 values different, all non-existing, they all match to the single blank row which is created in the model. The next slide, hopefully it's useful to see the difference. I created a few measures. One does a count rows distinct, the other one does a count rows of values, then count rows of all, and count rows of all no blank row. And then I put everything in a pivot table. And you see that count rows of distinct, since distinct does not consider the blank row, you see 1, 1, 1, then blank, and it aggregates for 3. Whereas if I do a count rows of values, since values considers the blank row as a valid row, I have 1, 1, 1, 1, and then 4 as the total. The same happens for if I do a count rows of all, or if I do a count rows of all no blank row. It is not so important to remember all these details, but it is important to know that this happens because for sure at some point you will compute some ratio between count rows and count rows of all, or count rows of values, or count rows of all no blank row. And if the result is 99.99999%, it means that you are using a function that considers the blank row somewhere, and the function that does not consider the blank row somewhere else. So either you fix your model, which is always the best option, so that all relationships are followed in the right way, or if you have issues with your model, at least you use the function that computes the correct number. In DAX, all the table functions return tables, but these tables are not just the values. These tables are the real tables. So imagine that I write an expression which is slightly more complex than the previous one. I do a sum x over filter of category, where I count rows for each category, the related table product, and I check if it's greater than 10. So it filters category, and then for each category it counts rows the related table product. That is fine. The result of this is a set of categories. But it's not just the category names. It's not just the category values. They are the categories. So the result of this filter is then used inside sum x. And when I write sum x over related table sales, this related table to which relationship is going to follow? Because the result of the first filter is a table containing categories, these are the sales of the given category, so the currently iterated category by sum x over the result of filter. So filter returns a table. The table inherits all the relationships that it has in the model. In-SQL relationships are not part of the model. You can define them as foreign keys, but then you need to specify a relationship in every query. In DAX, relationships are part of the model, and you don't need to specify them. Whenever you use a function that returns a table, the table return has all the relationships with the rest of the model, and you can trust it. So you can use related table sales, knowing that these are the sales of the currently iterated results. So the full function basically returns you the sales of categories that contain more than 10 products. Make sense? It's intuitive. I mean, it's not hard. It's not complex to read and use. It's only a bit delicate to you understand and use. The last thing that I want to show you about calculated tables is that table functions is that the result of any table functions can then be used inside your model. So if we switch for a second to the demo machine, oh, you're right, sorry. I was looking there thinking that it was the wrong place. Now you see that we have new column, we have new table, sorry, we have new measure, we have new column, but we also have new table. If you go to new table, you can create a new table and create, for example, a table containing red products. And red products might be a filter of the product table where product color equal red. Using an American keyboard is harder than expected. Okay. And you see that I have created a table which is called red products. It's there in my model. The point is that this table only contains red products. All the rest is gone. So it's a subset of the products. The table that I create in this way belongs to the model. So starting from this table, I can further create relationships with other tables. I can summarize, I can do nearly whatever I want. Calculated tables are not always useful, but when you need them, they become extremely useful. You typically use them to pre-aggregate values or to filter or to do summarizations, because keep in mind that the set of table functions that we have seen so far is just a basic set of table functions. In reality, there is a much richer set of table functions that you can use to summarize, to grab values, or to compute different expressions. And table functions are, besides, very useful if you want to test and experience. So you can, for example, create a table and you want to learn how values work or how all works. You can do all product color. This is a table expression, and if you confirm it, as a result, you see you get all the values of the product color. If you do all product color, all product brand, then you get, as a result, all the combinations of color and brand. And when you are learning DAX, when you are playing for the first time with table functions, it's very useful to use that just to test some features. Yes?
Would it be wise to use this to normalize a flat file?
The question is, would it be wise to use it to normalize a flat file? Well, you already know the answer, which is it depends. Let's say that the best way to perform operations on the data is not that of using calculated tables, but that of using Power Query, or how they call it today. So the query editor which exists in Power BI that you can use to do most of the ETL steps. Because in doing it this way, you avoid storing in the model the flat file, which probably is a very large one, but you only store in the model the already normalized and already well-defined data model that is then much easier. So it's smaller and probably faster to use. With that said, if we are speaking about a simple prototype or a single model that you want to do quick and dirty, then this is somewhat dirty, but it works just fine. So if you have a small model and you want to do things the fast way, this is totally fine. You can use a calculated table, and that works just fine. So calculated tables are, that's very usual. If your model is already well-defined, calculated tables are nearly useless because the data is already written in the correct form. That said, a lot of times you work on models that are not perfect. Data might come from reports, data might come from the web, and you have the option of using Power Query or using calculated tables. I would prefer using Power Query, but if I want to do something quicker and I'm familiar with DAX, then using a calculated table is totally fine. then I wouldn't build a data warehouse on top of that. So I would not do that in a corporate data warehouse. But for a small Power BI piece of code, that works just fine.